Well, hello and welcome, everybody. Hey, I really think it's cool. I get excited about doing these kinds of math problems, and out of nowhere comes a solution, and it's super clean, like pi, especially when it's irrational like that. That just kind of blows my mind. So, in this video, what we're going to do is we're going to do this problem on the left with this semicircle that has two smaller semicircles inside of it. And I'll leave this as a bonus here at the end, and I'll tell you where you can figure out, or you can find out how the solution for that one could be found. But for now, let's go ahead and dive into the problem we're going to do. So here's what we've got. We've got a large semicircle, and inside of it are two smaller semicircles, and this little segment here is tangent to both of the smaller semicircles, and its length from the bottom to the top is 2. Now, I found this on a Facebook math group. The author is Ayub Sobhani. I probably really said that wrong, but I apologize. Did my best. Anyway, I want to give credit to the author, so that's who came up with this problem that we're going to unpack here. So let's get into it. I think the best way to start is by kind of breaking down the composite part. So if we start with the large semicircle and say the whole thing's blue, and we take away the two smaller semicircles, what we would have is this blue shape that's on top right here like that. All right, now let's go ahead and dive in and label the things that we are going to be using. So let's say that the large circle has a diameter, or the larger of the interior semicircles has a diameter of A, and the smaller of the two has the diameter of B. Right? So we're going to name those, and that'll allow us to even talk about the radius and diameter of the biggest semicircle, right? So the area is 1/2 pi r squared. It's half because we have half of a circle. Now the radius for the big semicircle, well, that would be a plus b divided by 2, right? So the diameter would be a plus b divided by 2. That's our radius. So let's go ahead and plug that in. Here's what we got. Let's go ahead and clean up that half of pi. So pi over 2 times quantity a plus b divided by 2 squared. That would be the formula we're going to use for the area of the largest semicircle. And from that, we will take away the area of the smaller two. So let's talk about those, shall we? Now, the semicircle we'll call A with the diameter of A. So you take its radius, which is A divided by 2, you square it, right? And then times pi over 2. So pi r squared, half of it, right? Pi over 2. So pi over 2 times a squared over 4. Now, there's a reason we're going to leave it like that. We're going to do some simplification. So we could do, pi a squared over 8. We're going to leave it as it is. And we're going to do the same treatment for the smaller semicircle, right? So its radius would be half of b. Pi r squared would be the whole circle. We have half of it, so half of pi b squared over 4. All right. Now, this is how we said we were going to do it. The larger one minus the smaller two, right? Now, when we look here, we actually have a common factor of pi over 2 that we can factor out. And here's what we have left. So that's kind of cool. And a plus b over 2 squared would, of course, be a squared plus 2ab plus b squared over 4. So we're going to substitute that in over there, make ourselves some room. The denominator is 4 for all of them, so let's go ahead and put them all over 4. And we're going to rearrange so we can do some simplification. A squared minus a squared is 0. B squared minus b squared is, of course, also 0. So what we're left with is, inside the parentheses, 2ab over 4. So pi over 2 times 2ab over 4. That would be the area of the shaded region in blue. Let's go ahead and reduce those 2's. Those reduce, and what we have is pi times ab over 4. All right, that's pretty cool. Not quite good enough yet, because I would like to know what ab is. So let's explore this distance of 2 and see if we can come up with a numeric value of ab. All right. Now, if we took the two endpoints of the largest semicircle and made a triangle with a base, it would be a right triangle because, it's an inscribed triangle. It lies on the diameter. So that vertex up here would be the vertex of a 90-degree angle. So we have, right, angles. We have triangle MNAB. That's what we're going to call it right here, right? So that's a right triangle. That's pretty good. We can do all kinds of stuff with right triangles. And inside of this right triangle, we have two other right triangles, right? Let's see, right over here and here. So because we have a right triangle, let's do the Pythagorean theorem. A squared plus b squared is c squared. So c squared we're going to say is this side, and this is a, and this is b. So m squared plus n squared equals, right, a plus b squared. A plus b quantity squared is a squared plus 2ab plus b squared. All right. That's pretty cool. Now let's do the Pythagorean theorem for this one over here. here's what we've got. A squared plus b squared is c squared. Here, m is the hypotenuse, 2 is one leg, and a is another. So a squared plus 2 squared equals m squared. And let's do the same thing over here for this one, right? If you look at this triangle over here, hypotenuse is n. One leg is 2, the other leg is b. So a squared plus b squared is c squared would be b squared plus 2 squared equals n squared. All right, now we can do some substitution because you see we have an m squared here. We have an m squared there. We can substitute those things, and we have an n squared here and here. So we can just go ahead and do those substitutions like this, right? All right, that's pretty cool. So let's go ahead and get rid of those so we can start cleaning this up. You can see we can subtract a squared from both sides. Those will go away. We could do the same thing with the b squareds, and what we have is 2 squared plus 2 squared equals 2ab. Well, 2 squared is 4, so that's 4 plus 4 equals 2ab. So 8 equals 2ab, so ab equals 4. That's pretty cool, because our whole thing was AB over 4 times pi would be the area of the shaded region. So if we plug that in, man, that's 4 over 4, which is 1. 1 pi is the area of the shaded region. I think that is super, super cool. I think it's unbelievably cool. Now, there's another one. This one here. YouTube channel Math Paz or Paz, I'm not really sure. He has a really cool video on this one right here. He has his kid help share some of the mathematical ideas, which I think is kind of a neat thing. I went ahead and recreated the picture, but I'll let you watch his video on how to solve it. We've got a square with a side of 9, a quarter circle inside of it, a semicircle over here, and this little red circle. You have to find the area of that little red circle right there. So I'll leave a link to his video in my description below. And if you like this video, please do me the kind favor of like, subscribe, share, and especially comment. I really love to hear from you guys, hear what you're thinking, what you're liking, what you'd like to see next. And if you like to do a weekly math problem, check out my Substack. I've got one there just for fun. There's also some resources that are pertaining to that problem that you can use in your classroom for free that I post for you. I've got a website on teachingmath.org, all kinds of cool stuff there, some blogs, some resources, a lot of free stuff. And I have a Teachers Pay Teachers site. So if you're interested in using some innovative and very easy to use math resources in your classroom, please check that out as well. I'll leave links to all of that in the description. And until next time, I do hope you have a wonderful day.